Okay, good afternoon. Thank you everyone for coming. My name is Alan Gates. I'm one of the founders of Hortonworks, and despite that title, I'm actually still in engineering. I spend my time doing architecture and writing code. I actually do a lot of the architecture and kind of skunkworks type projects for Hive and a little bit for Pig these days. So I want to talk about some stuff we're doing to push to make Hive and Hbase work well together. So I don't usually put an agenda slide in because I like to kind of take you along for the ride and see, just let you kind of find out as we go along where we're going. But I think this is helpful because we're going to do a little bit of background before we get to the main goal here today. So what's the goal of this talk? The goal is to look at how do we take Apache projects that are out there, Hive, Hbase, Phoenix, and Calcite, and I'll go through what each of those are in case you haven't, if you're not familiar with all those. And how can we use those to start to build a single data store that we can do analytics with and transactional data with, right? Because today we have Hive, which you can use for analytics, and people do, and Hbase and with Phoenix on top you can use for more transactional type workloads. How can we push those together so that you can use those as an integrated system, and even why would you want to do that? Before we get there though, I wanted to spend a little bit of time talking about what is happening in Hive, some of the background, some things that are going on that will be useful to understand where we want to go with this, and some things happening in the Phoenix project that will also help you understand why we're pushing toward this and why this is interesting. So first of all, some things that are going on in Hive. So I'm going to make the assumption that most of you here are familiar with Hive, kind of what it does and all that, but basically it started out as a SQL engine to execute MapReduce jobs. That was its goal, that was what it was built for. Originally things took minutes or hours, that was fine, it was used for big batch. Starting with Hive 0.11, which was a couple years ago now, there was a real emphasis in making Hive good not only for those batch jobs, not just to do very large jobs that might take a long time, but also to support interactive and ad hoc queries where you're looking at much shorter time spans, where you want things to be measured in seconds or maybe even milliseconds. And so as a result of that work, we've actually gotten quite a bit of the way there. I don't think we're not done by any means, but we've pushed it down a long ways. So as part of that, you've seen a lot of new features added to Hive, the ORC file format. Hive now works with Parquet as well. Both of those are much more efficient storage formats for doing analytics. The addition of Tez and now more recently Spark as an engine underneath, both of which are much faster than MapReduce. Rewriting the operator pipeline to use vectorization, which is a much more efficient way to process data as it flows through your Hive jobs instead of one record at a time. As a result of a lot of these changes, as of Hive 0.14, which was released in November of last year, just as an example, one query from the TPC-DS data set that we like to use a lot, not use a lot, but we use that benchmark a lot. That's one of the ways we test Hive, make sure it's, each release is faster than the previous one. One of those queries from there, query 3, which is just a basic star join followed by a group, order, and limit. For a 200 gig data set, it finishes in 9 seconds. Now that's a toy-sized data set, right? That's just to kind of show what's basically the minimum time to set up and plan a query like this. And then for the 30 terabyte size, which is not toy, and this was done on a 20 node cluster where each node, I believe, had 256 gigs of RAM. So this doesn't fit in memory. We got down to 32 seconds. So we're getting there, right? We're not all the way there, but we're getting there. Pretty much any query though now in Hive, there's still about a 2 to 5 second floor. We can't get below that yet, and I'll talk more about why that is in a little bit. Our goal is to keep pushing that down. We want to get to the point where we don't have, where that floor is, say, 500 milliseconds or something, so that we can get in that truly interactive space. Because why do we want that? Because what do people want to do? They're sitting there working with their data on Hadoop, often through something like Tableau or Excel or whatever your favorite BI tool is, and they're just clicking through things, they're drilling down, whatever it is. They don't want to sit there and wait for that. Now, obviously, a 2 to 5 second floor, maybe even average query time of 10, 20 seconds, much, much better than what we had 2 years ago. 2 years ago when it was 2 to 5 minutes, nobody tried that, right? That was just awful. Now you can do it, but it's still not quite what you want. So we want to keep pushing that. So I want to talk a little bit about what we're doing to push that. And we're continuing to work on vectorization, which I won't go into in depth, but if you have questions about it, feel free to talk with me later. We're doing a lot of work on a system called LLAP, which I'll talk about in a little more depth. And we're switching to give the option to use Hbase to store the metadata. So what problem are we trying to solve with this thing called LLAP? And I'll explain more in depth exactly how it works. But basically the problem we have right now is, even with Tez or Spark, either one, Hive still has to spin up containers for every query. When you connect to Hive via JDBC or the command line, whatever you're going to do, there's still, and then you issue your first query, there's still some time where it has to spin up new containers to run that. That's just kind of the nature of Hadoop jobs. Now, you can in Tez do something where you pre-allocate your containers. When you connect, you say, give me 100 containers. Then you're just going to pay that cost once, and you keep them for the duration of your session. That way your next query won't pay that startup cost. You can drive that time well below that 2 to 5 second floor. Then you can start to get query responses that are very, very fast. But that's not very flexible, right? You might actually need less containers for your next query. You might need more. How do you know? There's no way the system can know, because you don't tell it what you're going to do, right? You just connect, ask for a certain number of containers, and then it has no idea how to adjust that. So it can be fast but not flexible. It can also be flexible, but then it's harder to be fast, right? It cannot hold on to those containers. You can tell the system, don't hold on to this, just give me what I need for this query and then give them back, and the next time I issue a query, give me the containers I need. But obviously, as I've said, that's not fast, because now it has to spend time doing allocations. Also, we don't have a good way to do caching of data between queries right now. And you might think to yourself, well, the OS cache will handle that for you, because you'll have read the data off disk. That may be true. You may be able to get some lift out of the OS cache, but transferring the data from the disk into memory is actually only a part of our I/O cost, and often not the biggest part. Often, the biggest part is actually deserializing the data from the disk format and getting it batched up in these vector batches so that it's ready to do vectorization. So we'd like to have a cache that handles that for us, that caches the data not in the serialized format that it's going to be on disk, but already ready to go into the operator pipeline. So what is LLAP? And by the way, I forgot to say, LLAP stands for live long and process. So yes, it is a joke from the Star Trek stuff. This is why you should never ever let your engineers name projects. This was named by one of the engineers in our Hive team. Somehow that name managed to stick, but just a warning, when you go back, let the marketing guys name your projects. Anyway, so what is LLAP? It is a daemon process that lives on your nodes concurrent with HDFS. So this would be on the same nodes as your HDFS machines. And the goal of this is to handle the caching and also to do early processing on the query. So it's multi-threaded, with some threads having the responsibility of doing the I/O elevator up off the disk, doing this deserialization, getting that in the cache, and then holding that data in memory, and some being given the responsibility of actually executing early operators on that data. So this would be filtering, projection, partial aggregation, partial sort, those kinds of tasks. Let me show you a little bit of how this would work. So if you have a Hive query here, you have HDFS. On these nodes, where the queries run, you would have LLAP servers that would then handle the front part of your query. Now, the important thing here is immediately you think, oh, this is just another MPP system, which it's not. This data in general is not shuffled between these LLAP servers. So we're not saying that you have to stand these up and then they handle all the query. You'd still use Tez or Spark or whatever you're using for your engine behind for any post-shuffle activity. So if you've got a hash join or a very large group by where you have to do a shuffle, something like that, that's still going to be handled in Tez or whatever as it is as today. The goal here is to speed up the beginning of the query, not the whole, not to get rid of the extensible nature of Hadoop, because one of the huge advantages Hadoop has is the fact that it can easily allocate and deallocate containers based on what your query needs, and that's much harder to do in a classical MPP architecture, right? So we're going for a hybrid model here where you have MPP-like in the initial set of tasks and then not in the post-shuffle tasks. So I already said why it's not MPP. It's not a replacement for Tez. It's not required. You can run Hive without it. To a first approximation, it's a standing map service, right? That's kind of what it provides for you. And this code is actually under development in a branch in the Hive project. You can go look at what's in there and play with it and just kind of get an idea of what it is and what it does. So now I'm going to change gears a little bit and talk about work we're doing with storing the metadata in Hbase. And again, let me say, trust me, this will all tie together and make sense on why I'm talking about this, because you might be thinking, why is he talking about LLAP? He said he was going to talk about Hbase. Trust me, all these threads will come together. Okay, so one of the next things we're working on that is relevant here is we want to make it so it's possible to store Hive's metadata in Hbase. Why are we concerned about this? So this is a pie chart that shows where we spent time on running one of those particular TPC-DS queries that I talked about. This big red stuff down here is the scan and join at the beginning, so LLAP will help quite a lot here, so you can see why we're spending time on that. It will also actually help here in dealing with the broadcast tables, because those could be cached. But you'll notice almost 28% of the time, and I believe the overall time for this was 13 seconds. So that means somewhere in the neighborhood of 3 seconds was spent planning the query. This is just getting metadata out of the catalog and planning it. So if we say that our goal is to get to query time that is 500 milliseconds, obviously we have to shrink this section as well, right? We can't just spend all our time in the back end and hope to get there. So that's why we're working on this. So what's the problem with, or what kind of problems are we facing? This is actually the ERP diagram of Hive's Metastore today. This is what happens when you let an ORM layer decide your schema layout for you. There's 40-some tables in there. Hive's Metastore only tracks, I think it's 7 or 8 actual types of objects: tables, databases, views, indexes, functions, roles. There's probably one I forgot in there, but I'm only at 6 or 7, right? And yet you end up with these 40-some tables. And even worse than that, in order to plan that query that I showed you, it actually takes over 700 queries against this Metastore to make that happen. No wonder it takes us 3 seconds to do all this work. That's just nasty. A lot of that time is actually spent in fetching the stats. That particular query I showed you has 1,800 partitions. It's trying to fetch stats to do planning, and so it's fetching those. And it's not super efficient, obviously, right now at fetching those in a good way. So what are we going to do about that? Or, well, let me talk a little bit more about, why is this a problem? So as is well known, I think, object relational modeling, ORM, it's an impedance mismatch, right? You have a set of Java objects, you want to record them to a database. Databases have a whole different set of rules and objects. That's why you get 7 or 8, whatever it is, fundamental types of objects and yet 40-some tables. So of course you could just say, well, I don't need Hbase, I'll just put it in SQL by myself, right? It's not immediately obvious that just because I want to get rid of ORM, I need to get rid of SQL as well. But that's kind of hard because Hive does allow users to have different kind of databases. Lots and lots of users have whatever their favorite database is, right? I'm sure if I took a survey here, some of you, if you're running Hive, some would have MySQL, some would have Oracle, some would have Postgres, some would have SQL Server. That comes down to what your company is comfortable with or what they usually run. I mean, at least we find that our users, when we go to them and start setting up Hive, they always come back and say, the DBAs say we have to have this type of database, right? We're not given a choice in that. So what does that mean? That means it's hard for us to do anything that is database specific. We have to keep it pretty general, right? Another thing, actually a huge thing, is one of the rules in Hive has always been that the metastore is never contacted from the task nodes. All the planning is done up front because there's always been the fear that the database can't keep up with the number of nodes. There's Hadoop clusters out there with 1,000, 2,000 or more task nodes, some up to 10,000. You just can't drive a relational database with that many connections, multiple queries going on at the same time. You'll knock it over, right? So that means you have to do all your planning up front. So what we're exploring is, can we use Hbase for this instead? So that gives us a number of options. One, we can just store objects as objects. We don't have to decompose them for relational stuff. We already know Hbase scales and performs, right? It's part of the Hadoop family, so that's second nature to it. We can start to store data in there that today we would be a little afraid to store just for size. For example, we can be much more aggressive in the stats we keep. And we can start to access the metadata from the cluster, from things like LLAP, without worrying about knocking over Hbase. So there's some objections to this, right? Hbase doesn't have transactions, the metastore needs them. That's a true statement, but people are working on this problem. There's a project called Tephra, driven by a company called Cask, that handles this. Yahoo also has a project called OMID2 that I'm working hard to get them to open source, so we can use that and play with it. There's other solutions out there. So this is a space where there's already a lot of innovation going on. People are solving this problem. I hear a lot that Hbase is hard to administer. When I had the Hbase team review my slides last week before I came, they said, no, it's not. Why quit saying that? So I don't know. I'll let you make the decision on whether you think it is or not, because I've had people tell me it is. But the point is, one way or another, these are problems we need to solve anyway, right? This is just classic dog fooding, right? Anything that we solve in making Hbase better for this is good for the Hbase community, it's good for the Hadoop community, so it's all just bonus. So how are we doing that? What we've done so far is make a new implementation of RawStore for those of you who aren't deeply familiar with Hive's internals. Hive has an interface called RawStore that anybody can extend and implement to do the metadata connection to the database. We've made one for Hbase. We didn't make it default. We don't plan on making it default anytime soon, so you can certainly still use your relational database. So far, we have less than 10 tables in Hbase. We've highly optimized it for read latency, so for queries like select or for insert, update, delete type queries, it's very optimized for that. And any time that we needed to spend more effort to lay the data out properly so it'd be fast for read, we've done that and put that on the DDL statements. So things like grant role, for example, might take a little longer than it did in the past because we have to do some unrolling and laying out to figure out what all roles a user's in and all that. but we've laid it out that way. We're also adding very extensive caching. We want to minimize the number of trips to HBase. So you saw before the thing where we were saying it takes 700 queries to plan that, or 700 queries against the metastore to plan the one TPCDS 27 query. We want to get that down to where that's maybe 10 queries against the HBase system, or maybe even less. You should ask once for the table, you should ask once for all the partitions, and once for all the stats, the partitions, and once to figure out if the user has permissions to make that query, and that should be about it, right? So that's 4. We want to push that chattiness way, way down. This work is ongoing. It's out there. You can, again, it's in Hive. You can go, there's a branch called HBase Metastore. It does work for some definition of work, by which I mean you have to play nice with it and not do things it doesn't know how to do yet. But you can create and drop tables. You can query them. I've tested all that. This is an area of active development. Okay, so now another pivot. I said I was going to talk a little bit about stuff going on in Hive. I'm going to talk a little bit about stuff going on in Phoenix. What is Phoenix? Their Phoenix motto is putting the SQL back in NoSQL, which I kind of find amusing. But basically, it's a SQL layer on top of HBase. So the goal here is HBase is good at HBase is a key value store, right? So it's very good for fast lookup, fast update, fast writes, but it definitely puts a pretty low-level model onto its users. A lot of people want to continue to use SQL, and so that's what Phoenix is there for. The goal is to basically provide you a transactional type, a SQL for transactional type processing in the Hadoop world. Now, as is always the case, Phoenix started in one place, which is the transaction processing, but there's a lot of pressure on it to move toward more analytics types work, right? People get their data in there, they store it, they like that, it's good, it's doing what they want, but now they discover they want to do analytics, and when the answer is, well, okay, in order to do analytics, now you have to move it over to Hive, or pick whatever your favorite analytics system is. Well, that's painful. Now you got data movement and you've got lag and all kinds of stuff. And people are saying, you know what, I just want to drive my reporting dashboard and I want it to be as up to date as I can, and it would be a lot more efficient if I could do my analytics in Phoenix. So there's more and more push to start to do those analytics type SQL in Phoenix, which is going to be a long road for the Phoenix project, right? Because there's a lot of stuff to add there. They are also working on adding transactions as I said before, with the work that's gone on to add transactions to HBase, the Phoenix community is involved in that and would like to make use of it. And then finally, and very interesting for us, is Phoenix is moving to use Apache Calcite. Now, for those who aren't familiar with the Calcite project, it's basically a tool that helps you build an optimizer for your SQL engine. Hive already uses it, has used it for 9 to 12 months now, I don't remember exactly. Basically, Calcite is a cost-based optimizer plus a set of default rules, and it makes it pretty easy for you to build new rules in your system, right? So when you put it in your system, you get kind of the basic rules like always push filters in front of joins, those kind of things come with it. But it also makes it easy for you to define, okay, what's the cost model in my system? How do I want to cost these queries? All that kind of stuff. This is important because cost-based optimizers actually aren't easy to build, in case you didn't know that. In fact, I saw a slide deck by, I think it was David DeWitt, who his comment on cost-based optimizers is, this isn't rocket science. When people can't do this, then we tell them to go do rocket science. So these are hard to build. So finding a project that's already working on this and sharing it makes a lot of sense. And the fact that both Hive and Phoenix are using this will become very useful. All right, so all that background, now we'll actually get to how can we use all this to push stuff together? Why is this useful? So let's just dream a bit. What if instead of having two separate projects, we had something where you could share a lot of what these guys are doing, right? Since we're seeing a lot of kind of convergence of some of these projects, what if there was a way we could share an ODBC and JDBC driver so users didn't have to think about what to connect to before they didn't have to put their data for one thing in one system and their data for the other in a different system. They could just put it in the system and then let the system worry about where to exactly store it. What if we could share one SQL dialect so you didn't have to worry about, I write queries this way in this SQL. If I'm going to use Phoenix, I write it in this other SQL if I'm going to use Hive. What if the Phoenix project could leverage the extensive analytics work that's already gone into Hive, right? Early on, I talked about a lot of the work Hive's done to make analytics work well in Hive. If the Phoenix project could leverage that instead of reinventing that wheel, that would give them a huge leg up, right? They'd save themselves a couple of years worth of work. And what if users could access their transactional and analytics data in a single system so they didn't have to deal with as much with data movement, and even they could do queries that span that, right? You might have some reporting query that looks some at your analytical tables and some at your transactional tables to give you a look at what's happening right now. What if we could push all that together? So how might we make that happen? There's kind of three insights here that we need to see to get an idea of how this might start to work. One, to a first approximation, LLAP is a storage server brings along some operators, like I said, filter, project, aggregate, sort. There's no reason, if we define this well, we can't swap this out for other storage systems, right? We don't need to build it in such a way that it's LLAP only. We can build it in a way that you can swap it out. Second insight is that we're using Tez or Spark or whatever behind LLAP to do post-shuffle operations. That's independent of LLAP. So if we put Hbase in that slot, there's no reason we couldn't use these things behind Hbase to do exactly the same thing. And third one is that Calcite, which I've already said is being used by both Hive and Phoenix, was actually designed specifically to enable integration of disparate systems. So part of its costing models in its cost-based optimizer is to say, okay, I know that this particular system handles this type of query better than this other system, so I should do it here or I should do it there. It actually can understand that in its costing. So it actually looks like a really good tool to help do this integration. Okay, so now I want to stress that the earlier work I talked about, things in LLAP and Hbase, putting the metastore in Hbase, Phoenix, all that's actually ongoing work. It's real stuff. This is vision, future slideware. So just being completely upfront about that there's no place you can go find this code yet. But this is where we think that we can go with this. So what if you saw the picture earlier where you had LLAP running on nodes? What if Hbase was another option there? What if when a user comes to Hive, he says, create a table, and I think this table is going to be transactional, so store it in Hbase, or I think this table is mostly analytic, so store it in LLAP, but that's the last time you have to worry about that, right? Queries then get split up. When they come into the system understands where they're stored, and it executes them where they are. So if they're in HDFS, it'll execute it against LLAP. If it's in Hbase, they'll execute it there. It'll use Tez and or whatever to handle post-shuffle operations regardless of the storage system. And we can leverage all the work that Phoenix has done in Hbase in order to provide these operators that match what LLAP does. There's already Phoenix operators to do aggregation, to do filtering, to do sorting, all that stuff. So there's not tons and tons of code here to write to make that happen. All we have to do is integrate with what Phoenix has already done. So what we get then is one system where the user still has to be a little bit aware of what they're doing. Transactions will work better in Hbase, but they'll work in LLAP if you need them to. Hive already supports transactions. Analytics will work better in LLAP, but they'll work in Hbase if you need them to. If you have a table that you need to do some analytics on, that'll still work. And Calcite will tie that all together with the query planning. So in the name of honesty, there's a few hurdles here. This isn't just like, oh, we'll go do this and it'll be no problem. We got to figure out how do we integrate the types and data representation between these systems. They're close. They're actually very close, but they're not right on. So there's a little bit of work to do that efficiently without having to actually change around the type representations. Both systems have, or will soon have, transactions. How are we going to integrate those so that it's seamless for users? And then to date, Calcite is mostly, it is a cost-based optimizer, but it's mostly focused around data warehousing, analytics type queries. That's where most of its background is. So there'll be some work there to make it a good optimizer also for transactional queries, right? Because it's actually a different set of problems. In analytics type queries, you tend to be focused on, okay, how can I minimize the size of my intermediate results so that I'm shuffling less data between operators or between machines. In transactional queries, you tend to be focused on, okay, what's the fastest access path to that one or those 50 records or whatever I'm looking for? Should I go through this index or that index or whatever? It's a little bit different set of problems, so there'll be some work there to make that happen. So didn't want to leave you with the impression that, hey, that it's all easy. There's some definite work to do, but we think this is a compelling vision of how we could start to push these two together. With that, any questions? Yes? Go ahead. I think he's got a mic there for you, so everybody can hear you.
You're going to work on integrating transactions in Hbase, right?
Well, actually, others are already.
Yes,
the you is the.
When I say you, I mean in general. I mean
yeah, you is in the community, not you as in me.
Yeah.
Yes, agreed.
So yeah, actually, for me, there is maybe it's a naive question. If you use a relational database, you can put everything in a big blob field, and you can get almost the same results, or not? Are you going for some specific reason to Hbase, or because also you're going to contribute to the community with having transactions in Hbase? Do you know?
Yeah, so I mean, it's a very fair question. Why not just stick it in a blob? So it comes down to the stuff. Well, one, because we think going to Hbase for the metastore helps enable this, right? It becomes a first step toward this. But the bigger one is what I talked about of we want to be able to access the database from the cluster. And that I don't think we could solve by just putting it in a blob. I agree that, well, and there's actually a second problem. Databases tend to store blobs in out of row. And so the access for a blob is generally slower than in-row access. So you probably wouldn't actually do it in a blob. You'd probably do it in some kind of byte string or something. But it's the same general idea, right? Yeah, you could do that, but then you don't get your ability to do from cluster stuff, and it gets harder to store bigger stats. Like we want to start storing histograms, and that we're just worried about the size of what we could fit in there. I think there was a question behind you.
What's the timeline for this?
Okay, what's the timeline? So I'm going to give you all those disclaimers and all that jazz. But the Hbase Metastore work and the LLAP work, we hope to have some kind of early beta type stuff by June, right? So I don't know yet how that will be released, but that's the goal. And then hopefully we would have it actually production ready by end of the year. The timeline on this is fuzzier because it's more work, but our hope is to have some kind of beta or probably even alpha actually by the end of the year. Yeah.
Speaking from practical point of my personal work, I see really major block from any transactional and normally work that is taken by RDBMS in Hbase is secondary indexing, and it stays completely unopened issue and no good solution inside Hbase, Hive, and so on. Do you plan to do something with it?
Yes. Yeah, actually, that's a really good point. I should have put that on the Phoenix slide. So the Phoenix community is already working on secondary indexes, and that's exactly why they're interested in transactions, because you can't build reliable secondary indexes without a transaction management. So that's actually their first use case for the transaction manager. So yeah, that is, I am not, I mean, I've talked briefly with the people working on that. I'm not day-to-day involved with it, so I don't know how far along it is, but I know they are working on doing that.
I'm sorry, but Phoenix has really big complexity with linking against specific Hbase versions. They have really big packaging issues. What do they do with it?
That one I'll just have to say I don't know. I'm not involved enough with them to know how they handle the packaging issues. Other questions? All right, I see well, no, I've still got a couple minutes, so. Okay, anyway, do you go ahead.
Thank you, yeah. After all this work has been done, is this the point where the traditional RDBMS becomes obsolete, or?
Well, there's still a lot of features in an RDBMS that this wouldn't have, right? But I don't wake up in the morning thinking about killing Oracle. I wake up in the morning thinking about how to make my user's life easier to put all their data in. So no, I don't. My goal here isn't to say the RDBMS is obsolete. My goal is to say you can put all your data in Hadoop and do the things you want to do there, right? Whether it's transactional, whether it's analytic, whether it's stream processing, whatever your use case is. Because what we want to make real is the promise that all your data you can keep your data all in Hadoop, right? That's where we're going with this. All right, any other questions? All right, well, thank you very much.
Okay.